Hello, everyone. Welcome to session 13 on beams, part 1. In today's session, we are going to cover more content about beams and get into how they deform and how there are stresses inside of them due to bending moments. So by the end of today's session, we will be able to relate the radius of curvature of a beam to local strain, and we'll be able to think in terms of the tensile and compressive strains on kind of the top portion and the bottom portion of the beam. We will also be able to relate the internal moment to normal or bending stresses within a beam. So these could be tensile or compressive stresses, as shown here, where we have a bending moment being applied, and above kind of what we'll call a neutral surface or neutral axis, you see that we have compression. So we're doing this essentially, and the beam is getting compressed, and below it's in tension. So before we get into talking about strains and stresses, let's go back to being able to describe the bending moment and the shear force across a beam. This is a fairly straightforward example, and we're going to use the integral or differential forms of dv dx equals w and dm dx is equal to v. The first step is to create the model, which we've kind of done already. We have a point P load at the end of a beam. The second step is to perform external equilibrium, or it could be the first step of when you're trying to do equilibrium, however you want to look at it. But we need to look at what the reaction moment and the reaction force at the wall might be. So here's R, a reaction force, and then MR describes the reaction torque or moment that the wall provides. To counteract this moment being applied by P at a distance L away from the wall. We'll go ahead and do our equilibrium, apply the Newton's second law on the entire structure, starting with the forces, and we get simply that the reaction force at the wall is equal to the force P applied at the end of the beam. And we select a location about which we can do our summation of moments and setting them equal to 0. We've designated this O, and we'll say it's at the left side. And we have that MR, which is a positive moment because it's coming out of the page, minus PL, that PL being a negative 1 because it's going into the page, is equal to 0. So MR is equal to PL. Okay, by this point, you've seen this type of thing before. Now, since we're going to use the integral or differential method of doing the graphing of the shear force and bending moment, let's go ahead and use the values at the ends of the beam. So what are we talking about here? We're talking about looking at the internal bending moment and the internal shear force close to the left side and close to the right side. So at the left end, what we have already shown is that we have an MR and an R. We calculated those out using external equilibrium. We could designate, say, an X1 or an X going from left to right for a coordinate system. And this really can be visualized as being kind of much closer to the left side. Okay, it's a little bit long for how we often draw these, but we're going to look just at the left end and say, okay, there's internal shear force using the convention. It's down when we've covered the right or we're exposed the right, and M is positive when we're exposing the right as well. So for a small x1, kind of close to this side, what do we see? We see, well, this R and V, they have to balance out with each other. So we can say that the internal shear force at the left side, or very close to it, is just going to be equal to R, and is also equal to P. We can also look at the relationship for this MR and M, okay? And we know that MR is equal to PL, In this case, we have mr plus m is equal to 0. So that means that m is going to be equal to minus mr, which is saying that m is going to be equal to minus pl at the left side. Let's go to the right side. At the right end, what we have is this force P acting. And we have, doing a cut, maybe we'll call this x2, coming from the right going to the left. And then we follow the convention where we say, okay, m, if you're covering up the left side, m is going to be negative or in the negative direction, and v is going to be going up. Okay, now we've talked about this before, how these V's and V's and V's and the M's and M's are the same, okay? But this is, and you don't have to necessarily use Hibbeler's convention, but we're going to use it for this class. CDL does it a little bit differently with the V's being flipped in the opposite direction. And it's good to choose a chosen way, or that's repetitive. It's good to stick to one way of doing things. And when we do the plots, we want to stick to this convention so that it's easy to communicate what we mean when we plot the shear force and bending moments. So at the right side, what we have here is an opportunity to equate this internal shear force to whatever vertical loads are on it. It's a free end, but it has P acting on it. So maybe it's not quite that free. So V at the right is equal to P. And just pointing out here that you could think of it as V of, x1 if you're using this side, x1 equal L. Or if we're going from the right side, x2 would be equal to 0. Similarly, we can write out an equation for the bending moment, and there is nothing happening here, so m is going to be equal to 0. Now, let's go ahead and use the dv dx is equal to w formula and use it in the integral form. So we have v is equal to the integral of w dx. W, though, is equal to 0. There's no distributed force on top of this beam. And so we do the integration, and this would be 0, but we still have the opportunity to put a constant. So we'll say C1. Now, what is the boundary condition at the left side? We said it's V is equal to P. So this V has to equal to P when x is equal to 0. So C1 is just going to be equal to P. We can go ahead and plot out. There's no additional, discontinuity or anything in the middle. So we can go ahead and say it's going to be a constant P across the entire length of the beam. Now, let's integrate dv dx is equal to m. I'm sorry, dm dx is equal to v. Oops. So that means that we can say m is equal to the integral dv dx. When we do this out, we take this coefficient, we make this the coefficient, so c1x plus another constant, and we have that m of 0 at the left side already from our boundary condition right here, yes, is equal to minus PL. So we need to plug something in, right? When x is equal to 0, we need to plug something into C2. It'll make it equal to minus PL. Well, C2 can just be minus PL. And when we plot our moment as a function of x, what are we going to see? We're going to see that, well, m starts off at a minus PL, okay? And look at this. C1 is equal to P, right? And if I plug in x equals L, then I have PL minus PL, so it's going to go to 0. And that also helps us satisfy the boundary condition, or allows us to satisfy the boundary condition that we already prescribed here on the right end. Okay, so continuing and copying and pasting, what do we see? We see that we have our beam, we have some reaction moment, reaction force, we have internal shear, internal bending moment, we have those plotted. So if we take this beam and we just look at it, okay, this is a somewhat three-dimensional perspective. Here's the length of the beam, and we have our force P acting on the end. If we take this and we visualize a slice in this kind of pseudo 3D format, what do we expect to see? Well, we're going to some distance x, or we had used x1 as well as a coordinate, but this is the wall. We're coming out. And we know we have an internal shear force, right, given by P, whatever x is. And we also have a bending moment that's going from minus PL to 0. So let's graph this internally, or not graph it. Let's just kind of draw some arrows to describe what's happening. This P, right, is in the same direction, or this vector here is describing the internal shear force, V, and we gave it a value P because that's what it's equal to, okay? But that's the internal shear force along the beam. And what about M? So M is a little bit interesting, right? Because M would be going like this, okay? It would be like kind of curling up, but it's always negative, okay? And if we were at the wall, it would be minus PL. If we're like at x equals L over 2, right, it'd be something like minus PL over 2. So it scales down to 0 as a function of x, and it's negative. So instead of it drawing it the same direction that we have here, we can draw it coming down and just being px. Right? So why are we doing this? The reason we're doing this is because we're going to show in a few minutes that the strain and the bending stress, okay, so the strain is dependent on moment. Later in the next session, we'll also show dependence on the shear force, okay, but today we're focusing on the associated strain and stress with bending moment, okay, px. And you can kind of see here what's going to happen. This beam is going to be pushed down, or this end is being pushed down. It means it's going to kind of come like this. And it's kind of like, wait, this point and this point are going to get a little bit closer to each other. So the bottom is going to be in compression. This point and this point are going to get a little farther apart. So the top is going to be in tension, or there'll be positive strain on the top. Let's do some math, though, to be able to get to these descriptions for strain and stress. We're going to first start with strain, okay, in this part of the session. In the next part, then we'll talk about stress. So deformation due to bending, okay, or strain due to bending, okay. But usually deformation, we're thinking, units of meters, and then strain is ending up to be unitless. And deflection will be something we talk about later. Okay, but let's kind of get some ideas of what the overall shape is going to be, and we're going to describe how we can look at strain along a beam, okay, with this change in shape. So we apply moments to a beam, okay, that's nice. And they're about an axis perpendicular to the axis of symmetry, right? So we have two options. They could be kind of about an axis going this direction, or it could be about an axis going this direction, right? So you could be like twisting it, or you could be bending it, all right, up and down. So here we describe our coordinate system. Usually x is coming out, y is this way, And usually we're talking about MZ, okay, which is causing some deformation. You can also do beam bending problems where you have MY, but for now we're not going to think about that too much. So what happens when we apply MZ? Well, it in this case is going to kind of curve up as we see here, right? We can have our same coordinate system coming out of the end, and we can have our MZ still being applied, but you see that it's like curving up. Okay, I should have grabbed something. Okay, what can I grab? Yeah, you know, it's bending moments are being applied like this, and so it's curving up. Now, it's kind of clear that, say, a point on top, right, is going to be undergoing some type of compression, and on the point on the bottom is undergoing some kind of tension. It turns out, though, there's something in the middle, okay, a surface that does not deform, and we call that the neutral surface, okay, along here, okay. So it curves, okay, but it does not change its longitudinal length along the beam. Above and below, though, there can be tension and compression. So one section will go into tension. The section below the neutral axis, in this case, for this internal bending moment, that is positive. Okay, see that? So it's causing the bottom to stretch out a little bit in tension. And then it's almost like this arrow is pushing into the top portion and compressing it. Okay, and so that's what we see here. So let's get a little bit more in depth in looking at the geometry and assigning some parameters. Say we have A, B, C, and D, E, F, and then now we apply a moment, okay, that's going to cause it to kind of smile. What do we see? We see that A and B are going to get a little bit closer to each other, and D and E are going to get maybe a little bit farther from each other. B and C will get a little bit closer to each other, and E and F are going to get a little bit farther from each other. Okay, and so we could, maybe it'd be better to call this A1, B1, C1, D1, but let's just call them D1, E1, and F1. And above we can call them A1, B1, C1, and we can also assign a point O where we have a circle essentially being formed with radius rho. So this rho is a radius of curvature that we can apply to this entire beam. This beam is having MB applied to it, so M is constant throughout, but you can have different sections of a beam with different radii of curvature, okay, as M varies, okay, as the radius of curvature varies. So here's our radius of curvature, and let's say that we can also describe the angles here, delta theta, between A1 and B1, and we could say, okay, delta theta is the same between B1 and C1. So these lengths were the same before we did the bending, and the A1 B1 length is going to be the same as the B1 C1 length. D1 E1 length is going to be the same as the E1 F1 length, but these lengths are going to be a little bit longer on the bottom, but we can describe them with these delta thetas. This axis, okay, we described a neutral surface before, We can also think of, in this 2D perspective, we can think of this as being a curve, all right? And Hibbeler calls this the longitudinal axis, right? This is the axis where you don't have stretching or compressing. And CDL calls this the neutral axis. So now let's go a little bit further and begin to look at what would be happening on a slice or an element. So imagine that this is a slice, and it could be, I didn't draw it this way, but it could have A, B, E, D at its corners. Okay, so it's like one of these blocks, and this is the beam. So this slice has width delta x, and we can draw a longitudinal axis, right? It's the one that's going through here, as you see here. And we can say that delta x is the initial width. And then we can also say that there's a delta s at some distance y from the longitudinal axis. So here, delta s and delta x are equal to 0 because this is an undeformed state. And as I change y, delta s is not going to change. But what happens when we introduce deformation as we did previously? Okay, so now this element is no longer a nice rectangle or square. It's a poor square, I guess. With all these angles, all four angles being 90 degrees, what do we have happening? We have A1, B1 getting closer, D1, E1 getting farther apart, and we can look at a deformed element. So what's going to happen here? Well, you can kind of get an idea that delta S is no longer going to be a constant as a function of y, this distance from the longitudinal axis. And we have an angle, delta theta, that describes the cut, or the portion of a circle on which this cut or this slice sits. And once again, we have a radius of curvature. Now, where does this radius of curvature typically go? We typically call it as going to the longitudinal axis. So maybe, it could be a little bit higher, but it's going to not, we're not describing it to this surface or this surface. We're typically thinking of this radius of curvature going to the longitudinal axis, where there is no stretching or compression. This width here was delta x originally, and on the longitudinal axis, it stays delta x. Okay, so along the longitudinal axis, delta x is unchanged. But we have an idea that, some other things could be changing. We already hinted at that delta s could be changing. And delta s could be changing as a function of the distance from the neutral axis. So y is that distance? Going toward the center of the circle, that distance, right, is going to be decreasing from this side to this side. On the other side, if y were negative, okay, we would see that this delta s would be larger. So we'll call this new length delta s prime. Okay, so we have delta s equal delta x, and now we've deformed it, and we have delta s prime. Okay, so here is the same picture that we just had. Delta s prime is that distance. This is the unchanged longitudinal axis, delta x along the longitudinal axis. And we can begin to think about what is happening. Okay, how is delta s prime changing at some distance y from the longitudinal axis. And how does this delta y, or this y and delta s prime, how are they related to each other? Well, looks like they could be related somehow through the radius of curvature. So let's explore this a little bit further, saying we want to define not just the change in length, delta s prime, but we're going to think about the strain. Okay, what is strain? Strain is a change in length over initial length. So we said previously, right, we had a delta x that's unchanged. So that's a pretty good initial length. That delta x we defined to be delta s. So these are the unchanged lengths, delta s. And the change in length is the delta s prime. So we can say, all right, what is the delta s prime? What is this? What is this new length minus the original length divided by the original length? Okay. So these deltas, I guess I should be careful. When I was saying delta, I was saying it was like a change, right? But really, we're using it here to say, okay, it's a small portion of the beam. So delta s prime minus delta s divided by delta s. Delta s we said was equal to delta x. We can define delta x, interestingly, right, as being rho times delta theta. Okay, right? Rho times 2 pi would be the circumference of this enormous circle that is not going to fit on, well, it might, it could maybe fit on the screen, but these radii are typically much larger than the beam height or thickness. So we have an unchanged delta x rho, which is equal to rho delta theta, and we have a delta s prime, which is different. Look at this. We know what our delta theta is. And if we go up a little bit from the longitudinal axis, we could define a new radius, okay, to this curve that has with delta s prime as being, what's the new radius? Rho minus y. So rho minus y times delta theta is actually delta s prime. Now let's do a little bit of algebra, a little bit of substitution. So delta s prime, okay, is this rho minus y delta theta. So that's right here. We have a delta s, which is just the rho delta theta. We have that in the denominator as well. So that's rho delta theta. What do? We see that, oh, we can get rid of all these delta thetas. And we can also see that we have a rho and a rho over rho. And we can describe the longitudinal strain, or strain along the longitudinal axis, as being equal to minus y over rho. So this equation is important. You should go ahead and write it down on your formula sheet. It turns out it's not one of the top ones that we'll use, but we're going to use it in a few minutes to derive some more heavily used forms of equations for describing bending of a beam. So there are some assumptions for beam bending. Okay, one is that the longitudinal axis on the neutral surface, this one, does not change its length. Okay, it curves, and we've discussed that a little bit already. That is an assumption. And another thing is that all the cross-section planes, okay, so if you took a plane, okay, or you look at this as a plane right here, or this as a plane right here, not a flying plane, but, you know, a geometrical plane, the longitudinal axis, okay, is perpendicular to that surface. So for all cross-section planes, that surface or this surface, there's going to be a longitudinal axis coming out perpendicular to it. And we're also going to ignore, okay, any deformation of the cross-section within its own plane. So yes, we showed that there could be deformation, and we'll describe actually the Poisson's ratio effect pretty soon on kind of this cross section. But we are, for our purposes, when we do much of our calculations, which we'll do in a little bit, not today for deflection, but for stress at least, we're going to ignore any deformation in the cross section of the plane. Okay. Now, what do we want to do? We would like to keep this negative y over rho, okay, relationship in mind. And we don't have something that really relates to our applied moment at this point, but we can think about the strain as being a maximum at a given location and a minimum at the longitudinal axis. Okay. If you recall, this is not too dissimilar for when we were describing shear strain on a twisted shaft. We were saying, hey, when rho is equal to 0, then there's no strain there. Okay? And it was maxing out at the surface. Now, this is a different rho. Okay, let's not confuse them. And we're talking about bending moments, and we're talking about normal strains, not shear strains. Okay, so it's very different. But we can begin to think that the maximum strains that we're going to see are going to be at the surfaces. Okay, and if we draw, say, this deformed element, and we say the C here, remember that was kind of like the radius before for torsion, but it's a little bit different here. If we say C is half the width, or half the height, better said, of the beam, we can say that it's going to be where it's a max. So the strain is going to be a max. So if I had a minus, or if I have a y equal to c, right, that's 1. And so that's where I'm going to see the maximum strains, here and here. Now, what you'll begin to see when we do these beam bending problems is that sometimes we take a slice and we draw like a line, a slanted line through it. And that slanted line usually is referring to stresses, but it can also refer to strains. So what do you see here? We see that, okay, there's a maximum, and then all on this top, given the direction of the center of the circle, it's in compression, and then down here, it's on the other side of this dotted green, and it's in tension on the bottom. Okay, not sure if that's clear. Maybe I'll zoom in here just to try to make it a little more clear. Okay, so above the neutral axis, or the longitudinal axis, or the neutral surface, we have what we're calling to be compression. And then when we get on the other side, the line crosses through this kind of vertical line here that's often drawn, and it shows that once it's crossed through, it went from, if it were tension up here, or with this compression, it goes to the opposite. So it's going to tension here. Okay, so another thing to keep in mind, even though we haven't related the moments to like a quantitative, all right, value of strain at this point, okay, but if the sign, the direction, if we have a positive internal moment, okay, that's going to put the top in compression, okay, and the bottom will be in tension. Now, let's look at a cantilevered beam with an applied moment, and this is just kind of emphasizing the same point again. If we had a moment being applied at the end, and this beam has a height of 2c, we might ask ourselves, where is the maximum bending strain? So here, and it got cut off, I'm sorry. Here, what we're saying is that the bending moment is a constant throughout. Okay, so there's kind of one radius associated with this beam, okay, because bending moment is constant, and the strain, okay, the longitudinal strain can be thought of with this expression, right? That is minus y over rho. Okay, so if we get to c above or c below, okay, that's where we expect to see some epsilon maxes. All right, so that's pretty much what we want to keep in mind. This is kind of a little bit more of a detailed graphical interpretation, but here's the M. And if you were to draw the bending moment diagram, we say, oh, there's no shear force and there's a reaction moment to this applied M, okay, on the right side. So just a little bit more detail, but we can plug in, like we were saying, or I was saying, is we can plug in y equals c or minus c, okay, this, to get to the top or the bottom, and that's where we're going to see the maximum bending strain, okay, where y is equal to plus or minus c. And we can also think, well, if the strain is a maximum here, okay, and this is a normal strain, we can begin to think, and we won't do this, we'll do this soon, but if there's an elastic modulus for this material, right, we could relate this strain to a stress. And where we see maximum strains, we're going to see maximum stresses as well. Now, we kind of suggested earlier that the top, if you have a positive internal moment, the top goes in compression and the bottom goes in tension. Actually, we more than suggested that we said this, okay? And it turns out we can kind of think about how much fatter or wider the top is going to get and how much narrower it's going to get on the bottom through the Poisson's ratio, right? So if we know what the strain is up here along in the x direction, right, we can describe what the strains will be in orthogonal directions, in the y direction, right, and also in the z direction. Now, why is this negative? Well, look, this is in compression here. So epsilon x, if epsilon x is like negative 0.01%, something like that, okay, then above here, okay, in the y direction, okay, it's going to be negative, negative. So it will end up being positive. There's going to be a positive strain, okay? And that's because it's getting compressed. So it's getting, it's getting a little bit thicker. And if we're looking at in the z direction, it's getting a little bit wider above, okay? So you get like a double negative happening here, okay? So you end up getting positive epsilon z, positive epsilon y above the neutral surface when you have this applied mz. Well, this brings us to the question that we can ask. All right, so if we have the radius of curvature for a bending beam being rho, and the specified location is a distance y above the neutral axis, what is the longitudinal strain along the beam at the specified location? And if we were doing it in terms of numbers, we might specify that in percent. Now, if we have a Poisson's ratio for the material, say nu, we ask what is the corresponding strain in the vertical direction? Okay, so how much strain is it going to be having in the vertical direction based on our calculated longitudinal strain? Okay, and so that's going to be related to a negative Poisson ratio times that longitudinal strain. Okay, So this concludes our first portion. It's a little bit long, but hopefully it'll be helpful in terms of being able to relate the radius of curvature of a beam to the longitudinal strain and also the strains orthogonal to that longitudinal strain. And in the next session, we'll pick up looking at how we can calculate stress based on an applied bending moment. Thank you.